Welcome back. And this next part is talking about applications of normal distributions. We're going to take that normal curve we learned about in our last lesson, where the mu was 0 and the standard deviation was 1. And we're going to now apply it to different situations where hey, with IQs, the mean is 100, but we can still normalize those scores based upon z-scores. So we're now standardizing any normal distribution, and then it can be used the same as it was in our previous section. So our conversion formula, very important formula, you need to know this formula, is z. We know what z is. X is our data point, what we're looking for, minus mu, of course, the mean of the population, divided by sigma, which of course is the standard deviation of the population. Notice we always round z-scores to 2 decimal places, the same as before. So what we're doing is converting to a normal distribution. We're taking a non-standard normal distribution. That means mu is not equal to 0. Heck, let's just say that it could be that mu is equal to 98.6 because that's our mean body temperature. And we're just converting them to z-scores so that we can look at the areas under the curve for the standard normal distribution. So our procedure, yes, we're still going to sketch that normal curve. We're going to label the mean and any other x values, data values. Then we're going to shade the region representing that desired probability. Then we're going to, for each relevant x, we're going to find the boundary for the shaded region, and we're going to convert those x values to z-scores by using that formula. Then we're going to find the area just like we did back in the previous section. So we can use the table or we can use the calculator. So here we go. Here's an example from the Tall Clubs International. Tall Clubs International has a requirement that women must be at least 70 inches tall. So at least 70 inches tall. All of these are critical reading parts that you have to get. Given that women have normally distributed heights with a mean of 63.8 inches and a standard deviation of 2.6 inches, we're going to find the percentage of women who satisfy the height requirement so that they could be in the Tall Clubs International. So first, just like we did in the last section, we're going to draw that normal curve. And we know right in the center is mu, right in the center is our mean. So we have a mean of 63.8. We also know that the mean mu in our standard deviation is where z is equal to 0. We found that last time. Now it says that the standard deviation is 2.6 inches. So we know from the last section that this is a z of 1, we have a z of 2, we have a z of 3, and we can continue on here. A z of negative 1, a z of negative 2, and a z of negative 3. Well, we could go ahead and list all of the scores that would be based upon 63.8 being our mu. So if I have a standard deviation of 2.6 inches, that means from mu 63.8, when I go one standard deviation, I'm really going to add 2.6 inches. So I've got 63 0.8, and I'm going to add 2.6, and I know that Converting this to inches now, 1 standard deviation away, I'm going to have 66 inches. Because 63.8 plus 2.6 is not. 63.8, and I'm going to add 2.6, and for some reason my calculator keeps giving me the absolute wrong answer, and I know better. $89.8. Can't be. All we're doing is saying 63.8. We're going to add 2.6, 66.4. We're going to add 2.6 again and get 69.0. We're going to add 2.6 again, and 3 standard deviations away would equate to a woman being 71.6 inches tall. So I want to know, in this tall club, women need to be at least 70 inches tall. Well, I can look now right here at my sketch, and I know that 70 is greater than the 69 but less than the 71.6. So I know that 70 is going to fall right in here somewhere. So I know that I'm going to end up with a z-score somewhere between 2 and 3, more than 2 but less than 3. And I can use my conversion, that formula that said z is equal to my data point minus mu divided by the standard deviation. So z is equal to my data point, 70 is my data point, minus mu, 63.8. And then I'm going to divide that by standard deviation, and my standard deviation is 2.6. So I'll bring my calculator up, and we're going to do 70 minus 63.8, divide that by 2.6, and I find that my z-score is 2.3846. Of course, we're going to round that to 2 decimal places. So my z is 2, sorry, I lost my calculator, 2.38 is my z. Well, now that we know that z is equal to 2.38, we can go back up to our drawing, and it says at least. At least means it could be 70 or more. So the area that I'm going to shade is this little area here on this tail. Then we're simply going to go to our calculators just like we practiced in the previous section. And we're going to do second distribution. This time I have the z-score. I want the area. So I'm going to cursor down and do normal curve. I'm not coming from the end. Look at your picture. I'm coming from when z is 2.38, and I'm going to where the z gets to be as large as it can. So I'm going to punch in 2.38. My upper limit is going to be 9999, and I then can go ahead and hit paste. and I find that area is going to be 0.0087 when it's rounded. 0.0087. That is the area under the curve. That means there's 0.0087. And if I put that in percent, it's 0.87%. There's a less than 1% of the women that are tall enough to be in this Tall Clubs International. Now I'm going to go back to the calculator for a second, because the calculator will do all of this for you. And if you go to second distribution, back down to number 2, now I'm going to leave the lower as my actual data point. I'm going to put in my lower as being 70. I'm going to leave my upper, and I'm going to put the mean in as being 63.8 and my standard deviation of 2.6. And I'm going to get 0.0085. So very, very close, very, very close, even when I put the actual numbers into the calculator for the mean and the standard deviation. So I need to look at finding values from known areas. Again, we caution you, do not confuse z-scores and areas. Z's are distances along the horizontal. They are the distance away. It is a measurement, one standard deviation from the mean. Areas are regions. Those are the shaded areas of the normal curves. We have to remember what we are looking at, the right side or the left side of the graph. Z has to be negative on that left-hand side, and on the right-hand side must be positive. Areas or probabilities are always positive. Remember, probabilities are between 0 and 1. So this goes through the procedure for finding those values. We're again going to sketch that normal curve. We're going to put anything on there as we can, enter the probability percentage in the appropriate region. We're going to shade that. Identify what we're looking for. And we're going to refer to table A2 or use our calculators to identify the corresponding z-score. This formula, I'll be honest, I never use this formula. And it's just a manipulation of the other formula we've been using that says z is equal to x minus mu divided by the standard deviation. If you remember this one formula, you don't have to remember the other one. They're all the same. I just solved for x. Refer to the sketch that you've made and verify the solution makes sense. And that gives you a key as to you've got the right area and the right C. So when designing aircraft cabins, what cabin height would allow for 95% of man to stand without bumping their heads? Man heights are normally distributed with a mean of 69.5 inches and a standard deviation of 2.4 inches. So, of course, we're going to sketch. You know, that's always our first job. Right in the center there, we're going to put that the mean is 69.5. I always like to write my standard deviation of 2.4 inches out here. And I want 95% of men to be able to stand. So 95%, think about that, and I start highlighting away. 95%, well, this is only 50%, isn't it? Wow. So I need to go all the way over, and I need to go over and leave just one small amount over there that's about 5%, right? Because I want all these men to be able to stand. Right there. So this is 0.9500 is the area under the curve. Even though it's 0.95, if we still have the two zeros, it is the area under the curve. Because I have the area, I'm going to use the inverse. I can look up the area on my table, or I can use the inverse. My area is 0.9500. I have two options here. I can go ahead and go down and just use my area and hit enter, and it's going to give me my Z-score of 1.64. Now that I know my Z-score, I'm going to use my formula. Z is equal to x minus mu divided by the standard deviation. Let's fill in the blank. Z we found to be 1.64 is equal to x. Well, x is what I want. I want to know what those height of men at the 95th percentile. Minus mu, I've forgotten what mu is. I'm sorry, minus the standard deviation, which is 2.4. Mu is the mean, 69.5, divide by the standard deviation, which is 2.4. Well, I'm going to use algebra to solve this, of course. I'm going to multiply both sides of the equation by 2.4. So I've got 1.64 times 2.4, and I get 3.936. We've got the hourglass going on here, sorry. 3 point, it still doesn't want to work. Okay, we got 3.936 is our answer to that, is equal to x minus 69.5, and obviously we're just going to add 69.5 to both sides of the equation, and we'll find x is 73.44. It really doesn't like it when I don't use this calculator, huh? 73.44. So 73.44 inches needs to be the height of that cabin so that 95% of the men can stand without bumping their heads. So here we have IQ scores, and this truly is what we have found. IQ scores have a mean of 100 and a standard deviation of 15. So you know we're going to draw that normal curve. Here's mu. It's 100, and it's the same as 0 on a z-score. We know that z's positive here, and we know that z's are negative here. And we also know that with a 100 as a mu and a standard deviation of 15, adding 15 each time will be at the score of each standard deviation away. So a 115 IQ is one standard deviation in the positive, 130 is two standard deviations in the positive, etc. Now I also need to subtract, so I've got 85. Subtract again, I've got 70. Subtract again, I get 55. That looks like a negative 85. That's obviously not a negative 85. And I want to find the probability of an IQ which is less than 85. Less than 85, well here's my 85, and I want to find this probability. So what I first need to do is find the equivalent z-score. Well, I know the equivalent z-score because guess what? It's right on 1, so my z-score is equal to -1. I don't even need to do the calculation. And I can go to my calculator then and find the probability. Probability is area, so distribution, I have the z-score. I'm going down to the normal curve. I'm going to say all the way from the very end, and I'm going to go to the upper limit of -1. Then, of course, going to hit my enter button, and I'm going to find that the probability is 0.1587, or 15.87%. So there's not a lot of our population that have an IQ below 85. 50% are at 100 or less. Oh, we didn't do the other one. Find the probability of an IQ that's greater than 70. And it's not the requirement for being a statistics textbook author. This author just has a sense of humor. So if we looked at 70, that would be where Z is at -2. But this time we're greater than, so we would be coloring this area here for greater than. So when we go to our calculator, again, we have Z. So we're going to find the area by going to the distribution, going to the normal curve. My lower level here now is -2, and I want to go all the way to the end. So -2, and I'm going to put 9999999, and go ahead and hit enter. And I'm going to find out that that area is now 0.9772. 0.9772. In other words, 97.7% chance that someone has an IQ above 70. And these are still very similar, but I do want to look at this one because it's the opposite. Find the percentile of 90, which is the IQ score separating the bottom 90% and the top 10%. So I'm going to draw my normal curve. It always keeps me straight as to what I'm thinking about here. There's mu as being 100, z of 0. And I want the percentile being 90, the 90th percentile. So I want from the far end here, and I want all the way up to the 90th percentile. So I'm not going to have much left there again. So this is the 90th percentile. Again, if it's the 90th percentile, that means that the area here is 0.9000. And I want to know what the IQ score is that separate them. Of course, this is going to be 0.1000. Again, they have to add up to 1. So I'm going to go to my calculator. And now this time, remember, I have area and I want Z, so I'm going to go to second distribution, and I'm going to go to inverse norm. Norm, the area is 0.9000. coming all the way down and hit paste. That means my z-score is 1.28. Remember, round z-scores to 2 decimal places. 1.28. For some reason, it doesn't like to write after I have had my calculator up. Again, that's my z-score. Now I can translate that z-score, 1.28, is equal to x, because I want the z-score equal to 1.28 minus 100 times the standard deviation of 15. And of course, I can bring my calculator back here and say, hey, I want to take 1.28. I'm going to multiply that by 15 to clear the fractions, and I'll get 19.2 would be equal to x minus 100. Obviously, I'm going to add 100 to both sides and get 119.2 is equal to x. And IQ scores are in whole numbers. So my IQ of 119 would separate the 90th percentile and the 10% top. That concludes our section on the application of the normal curve. You'll be doing a lot of problems to get practice on this.